Welcome to the laser safety video, where we will introduce to you some of the hazards you may encounter when working with lasers and discuss how to work with lasers safely. This video will be divided into the following sections. To begin with, there will be a brief introduction to lasers and a summary of the main associated hazards when working with laser emission. This will be followed by an overview of the different laser classifications and what we mean by these classifications. Next, we will present the hazards associated with eye injuries and injuries to the skin when working with laser light. And finally, we will discuss some good practice procedures for working in a laser laboratory environment, as well as details on protective eyewear. The purpose of this video is to discuss some of the common hazards that can occur when working with lasers and what you can do to minimize the risks so that you can carry on working with lasers safely. This video will not be able to cover all of the risks associated with working in a laser laboratory, and since all laboratories are different, it is important that you also familiarize yourself with the appropriate general and lab-specific safety information in addition to this video prior to working in the lab. There will be a quiz for you to take at the end of the safety course. Lasers are sources of coherent light, which enables them to have both high output power as well as being highly directional. These properties have made lasers very useful for a large number of applications. However, they also form the basis for many of the associated hazards, and personal injuries can result if they are not handled correctly. The main hazards associated with laser emission include hazards for the eye, the skin, and hazards associated with combustible material. However, these are not the only risks associated with working within a laboratory environment. The most obvious risk when working with lasers are eye injuries. A laser beam viewed with the naked eye can lead to everything from being temporarily blinded, minor permanent blind spots, to becoming irreversibly blind. Since eye injuries are the major risk when working with lasers, the classification system for lasers is mainly based on the amount of exposure that the naked eye may be subjected to with only low risk of damage. The exposure limit that the naked eye can handle before protective eyewear must be worn is known as the maximum permissible exposure, or MPE limit, and depends on the wavelength of the light involved, the power of the beam, the pulse duration, and the laser beam properties. The distance that one must stand away from the laser source for the output beam to be below the MPE limit is known as the nominal ocular hazard distance, or NOHD. This distance can be small for low power or highly diverging beams, although it can be many kilometers in length for high power, highly collimated emission. Any laser that you work with will have an assigned laser classification based on a set of criteria that we'll summarize in a moment, along with some typical examples of lasers you might find in each of the classes. In general, when working with a new laser system, as a user, it is most likely not your job to assign a classification to the laser, but it is your job to know what should be expected from the class of laser you are using and how to work with it in a safe way. The laser classification is mainly related to the wavelength, output power, and for some classes, the beam properties of the laser. However, it does not include other hazards one might experience within a laboratory environment, such as electrocution or chemicals. Class 1 lasers are completely safe when operated under normal use and have an output power of less than 0.4 milliwatts. This class of laser includes toys and many laser pointers. However, lasers with higher power can also belong to this class, provided that they are fully enclosed and sealed or interlocked to prevent any dangerous beams from escaping. Examples include DVD players and printers. For Class 1 lasers, if viewed with the naked eye, the output of the system is below the maximum permissible exposure, or MPE limit, making them safe to use without protection. Class 2 lasers only include visible light lasers, ranging from 400 to 700 nanometers, and are safe to use due to the blink reflex. Class 2 lasers are limited to between 0.4 and 1 milliwatt of continuous light. Intentional viewing of Class 2 lasers, however, can lead to eye damage. Class 3R lasers are considered safe if handled correctly. For visible light, Class 3R lasers are limited to 5 milliwatts continuous emission. Class 3R lasers may be hazardous under direct and specular reflection viewing conditions, but are not normally hazardous for diffuse reflections. Class 3B lasers may be hazardous and must include both safety interlocks and a key switch. Lasers belonging to this class are more powerful than Class 3R lasers. However, they have an output power less than 500 milliwatts. Class 3B lasers may be hazardous under both direct and specular reflection viewing conditions. However, they normally are not hazardous for diffuse reflections. Class 3B lasers are often used in laser shows. However, they are too powerful to be used as laser pointers, and these should be avoided. In fact, you need permission to use these. The lasers enclosed in DVD players and printers are often Class 3B if taken out from their enclosures. Class 4 lasers have an output power greater than 500 milliwatts and are potentially dangerous. A direct beam is a hazard to both the eyes and skin. Even diffuse reflections from Class 4 lasers may be harmful. These lasers may also ignite combustible material. Class 4 lasers must include both safety interlocks and a key switch. Many scientific lasers are in this category, but also many lasers for surgery and material processing fall under Class 4. In addition, when using optical instruments such as focusing optics, the risks associated with lasers of different classes will increase. Class 1M lasers have a higher output power than Class 1 lasers, but are still safe to use since they have a larger beam diameter or larger beam divergence, such that the maximum permissible exposure, or MPE limit, cannot be exceeded unless imaging optics are used. Class 2M lasers have a higher output power than Class 2 lasers, but are less damaging than Class 3R, since the beam is larger or more divergent. This class is only for visible light, and the blink reflex will make these lasers safe, unless viewed through some optical instrument. In addition, there is also a Class 1C for cosmetic treatments that use lasers. This class has a higher output power than Class 1 lasers, but includes safety mechanisms that ensure the risk for eye injury is not higher than it is for Class 1 lasers. Depending on the class and specifications of the laser that you will operate, different eye-related hazards may dominate, since different wavelengths of light interact with different regions of the eye. Laser light can therefore be dangerous for the eye across the electromagnetic spectrum. However, one range that poses particular danger is visible light, spanning approximately 400 to 780 nanometers. Since the eye is designed to focus this light down onto the retina in the back of the eye to form an image. This means that lasers operating in the visible wavelength range can cause damage to the retina if the eye is exposed to the laser radiation. The damages are either photochemical or retinal burn. The visible frequencies only form a small part of the total electromagnetic spectrum, however, and even light that is not visible to humans can still be dangerous for the eye. In fact, non-visible radiation can pose additional hazards, since you cannot see where the radiation is, or in some cases even know that you are being hurt. Exposure to radiation in the far ultraviolet spectral region can cause photokeratitis, or sunburn of the eye, when in the wavelength region spanning approximately 180 to 315 nanometers. This can affect the cornea at the front of the eye, but also the skin. Light in the near ultraviolet wavelength region, spanning approximately 315 to 400 nanometers, will be absorbed by the lens in the eye and can cause photochemical cataract, or clouding of the eye lens. Exposure to the near-infrared wavelength range, spanning from approximately 780 to 1400 nanometers, also known as the NIR, cannot be seen, but will still be focused onto the retina in the back of the eye and may lead to cataract and retinal burns. Further into the infrared, between approximately 1.4 and 3 microns, known as the IR, exposure to these wavelengths can result in aqueous flare, which is abnormal protein in the aqueous humor, cataract, and corneal burn. Further still into the infrared, at wavelengths ranging from approximately 3 microns to 1 millimeter, exposure can lead to corneal burn. If you sustain retinal damage, your vision could end up looking something like this. If you develop cataract in the eye lens, your vision could end up looking something like this. As for any laser injury, the severity of the damage caused will depend on many factors, including the wavelength, power, exposure duration, and beam properties of the laser, as well as the type of exposure, be it a direct hit to the eye, specular or diffuse reflections, or long-term low-level exposure. In addition to eye damage, laser hazards also extend to the skin. When high-intensity radiation, or radiation of certain wavelengths, come into contact with the skin, damage can occur. This can result in burns to the top surface, subdermal burning or damage, or can lead to a risk of skin cancer for some regions of the ultraviolet spectrum. For all wavelengths, exposure to an intense laser beam can cause burns to the skin. However, other effects can also occur for different wavelength regions. Primarily, skin damage can occur when exposed to ultraviolet wavelengths, causing anything from sunburn and an increase in skin aging, increased pigmentation or pigment darkening, known as tanning, to occur, to an increased risk of skin cancer for some regions of the ultraviolet spectrum. When working with lasers, care should be taken to avoid irradiating the skin with the laser output, in particular for wavelengths that can cause cancer, or wavelength ranges that can cause damage without being able to feel it happening. Furthermore, photosensitive reactions can occur if the skin is irradiated by lasers with output wavelengths in the visible range. For a safe working environment, there are some general rules that should be followed when working with lasers. You should make sure that the room is equipped with the correct warning signs prior to starting work, and always turn on the laser warning light if a laser is operational inside the room to alert others. Any lasers should be appropriately labeled with their class type and safety warnings. Before you enter the room with the laser, you should remove all jewelry and watches that may reflect light from the laser if accidentally inserted into the beam path, and put on any laser safety eye protection that is required. If the laser warning light is on, knock on the door and wait for a response before entering the lab. Good practice when working with lasers includes ensuring that you keep the laser beam in a single horizontal plane below eye height. This will reduce the risk of eye injury. If you need to move your head through the plane with the laser, cover your eyes with your hand and duck below the laser plane. When coming back up, repeat the procedure. Make sure that the laser is enclosed. The material you use to enclose the laser, and also for the beam dumps, must be made out of material that will not ignite or melt if hit by the laser beam. When aligning a system, use an alignment laser if possible, or alternatively, reduce the power of your laser for this procedure. A good option may also be to use cameras when aligning the system, if possible, rather than doing it by eye. Remember that in low light conditions, the pupil in the eye will expand, which may change safety calculations. Always work with good lighting in the lab if possible. To protect the eye when working with lasers, specific eye protection may need to be worn. The type of protective eyewear will depend on the wavelength, power, pulse duration, and beam properties of the particular laser that you are using, and a safety assessment of the experiment and laser system must be performed to identify what level of protection is required for each activity. Laser goggles typically protect the eye in specific regions of the electromagnetic spectrum, but may have very little or no protection in other regions. When working with any laser system, in particular a new laser system, care must be taken to ensure that the correct protective goggles are selected each time for each different use. Some goggles that protect across a wide range of the visible spectrum may have a low transmission for the remaining spectrum. If you can use a pair of goggles that give sufficient protection but have a larger visible light transmission ratio, then this will make working in the lab easier and safer. Different regions of the world have different standards for laser goggle safety ratings. In Europe, your laser protective eyewear must conform to the EN 207 standards and must also contain the CE mark. A pair of laser goggles marked only with an optical density, or OD marking, are not permitted for use in Europe, since the standard requires that the power density of the laser is also considered in the safety calculation. Both the filter and the goggle frame are considered in the calculation, and since the worst-case scenario conditions are used, this does not allow for reduced eyewear protection outside of the nominal ocular hazard distance, or NOHD. The tables and information you can use to calculate what goggle rating you require for each different laser output or different laser application can be found in the material accompanying this video. The ratings are divided into different categories depending on the wavelength of the laser, the pulse duration, and the power density of the beam. If you do sustain a laser-related eye injury, seek expert medical advice immediately. All accidents or near misses, whether laser-related or not, should be reported immediately to continue improving the safety of the work environment. Thank you for listening to this laser safety video. This video has summarized the key hazards that can occur when working with lasers. Make sure to complete the rest of the laser safety training by reading through the additional material and take the quiz at the end to register your successful completion of the course.